Okay, so now I will share my screen. I hope all of you can see my screen, right? Hello, can anybody respond that can you see my screen?
Yes.
Okay, so this is first tutorial and we will discuss some of the questions. So as you can see, question 1 is about you have to see whether these four statements which I have written, are they true or false. So you can just try solving them. So first is group of order 31 is a billion. You have to see whether this is true or false. Group of order 4 is cyclic. And does there exist a billion group of order 2021 of this order, and a group of order 6 is a billion. So you can start thinking and you can start trying, and we can start discussion, like we can start discussing whether which of the following is true. So question is clear, right, to all of you? Yeah, in between you can keep responding, otherwise I feel like I'm the only one here.
31 is a prime number, therefore it is cyclic and therefore a billion.
Yeah, so that's correct. A part is true. So can you give explanation about the rest of the parts, why they are true or false?
Claims for group is order 4 and that is not cyclic.
Exactly right. So we have a client for group Z2 cross Z2, which is of course order 4 group, but it's a billion but not cyclic. So B part is not true. Very true. About C. Yes, what can you say about part C?
Is the 2021 is a prime number?
2021 is a prime number.
If it is a prime number, then it is automatically a billion. So there does not exist means there is a wrong statement.
Sorry, I didn't get you. So you said that Z2021, if you look at Z mod 2021Z, then that becomes a billion provided you have this number to be a prime number, right?
So if it is a prime number, then that group is cyclic and therefore a billion.
Okay, so this statement
so there
is
does
then,
not exist means it is a wrong statement.
yeah, so correct. So you know that Z mod NZ is a group for every n, right? In particular for this n also, and you can see that those are finite billion groups. So there does exist a billion group of that order, right? So okay. Because even if it is not prime, you can use that. Yeah, you can use that fact that since the number is, you can also say by that way also. But there does exist for every n, there exists in a group of order that, and you can see that if it is prime, then cyclic, and then a billion. Correct. So this statement is false. What about part D?
S3 is non-abelian.
S3 is, yes, this is the first non-abelian group that we have. So therefore there exists order 6 group which is non-abelian. So that is also false. So among these statement only part A is true. That's correct. Okay. So question 1, I guess it's clear, right, to all of you?
Yeah.
Okay, what can you say about question 2? So you have two sets I have written in terms of matrices. So these are, one is where you have upper triangular matrices, one is upper triangular with the diagonal entries to be one only, and remaining entries are from real. So you have to check whether that is a subgroup of GL2R, or can you quickly check it? Is it a subgroup? So in order to see subgroup, what do you need to check exactly? Just a moment, I will quickly go to if somebody is waiting. Okay. So is that, can you see it quickly whether that is a subgroup of GL2R? Sorry, but I have to keep looking at this lobby if people are there. Yeah, so can you say something about, yes, any of you? So are you there, all of you? Are you trying?
So T satisfies both closure as well as inverse axiom.
Right. So anyway, you can check that it satisfies all the properties to be a subgroup. It is closed under multiplication. Here the it's a matrix multiplication. The operation is, and clearly you can see that any two elements which are upper triangular, product is also upper triangular, and you can see identity element is there. Every element has inverse that you can write in the upper triangular matrix form. So yes, this is a subgroup indeed. So, but can you say whether this is a normal subgroup of GL2R? Yeah. I hope all of you are trying, right? Yeah, so I think we can discuss now. So, did you find any answer for this? That is that normal or not? Yes. Um, so okay, this is not actually not a normal subgroup. So can you give me one simple matrix? If you can conjugate this upper triangular subgroup by that, you will not land up inside T. So by the meaning of normality, you want to say that G inverse belongs to T for every H in T and G in GL2R. So can you give me that one G for which this conjugation G at G inverse is not in T? Yeah. Can you try with this matrix 0, 1, 1, 0? This is in vertical matrix, right? So what is G times any element of upper triangular times? You can see its inverse is the same matrix. So can you see what is the product of this? If I'm not wrong, then this should work. Can anybody quickly tell me the product?
It's C0BA.
It's a C0BA. This is what you're trying to say?
Yeah.
Okay, so does it belong to T?
No. If B were non-zero, then it will not be a T.
Yes. So the definition of normality means you have to conjugate G at G inverse should be in H for every H in H, right? So, but you can find an element in G and T such that the conjugation is not in T, right? So, therefore, T is not a normal subgroup. Is it okay? It, it's okay, right?
Yes.
Okay, so what can you say about normality of T in U in T? So we want to see whether U is a normal subgroup inside T. This is we want to see. This should be easy. Yes, who will tell this answer? Is it normal?
No, it's not normal.
So we want to check U is normal in T, not in G. So is it not normal in G? Sorry, T. T is upper triangular matrices. U is having diagonals to be 1 and still upper triangular matrices. So isn't U a normal subgroup of T? So it will be a normal subgroup. I think you can check once again. So I'll quickly write. If you see, in order to check the normality, you have to see uh, T U T inverse should be in U for every U in U, T in T, right? If you look at the 1x01 and what is the inverse? Here it will be A inverse something 0 C inverse, I guess. So something I have written at in the top. So if you will see what is the multiplication here, yes. If you see your this entry will be something after multiplying these two, and you will still remain A inverse C inverse. And if you multiply the first one with this, then you will get that it is 1 something here 0 something. It's again in U, right? Yeah.
Yes.
So yeah, so it's a normal subgroup. So this is a normal subgroup, however, T is not normal inside G. So question 2, I guess, is clear more or less. So we can go to question 3 now. So you have to, first part is you have to list all the abelian subgroups of order 36. So how will you see that? How to write all abelian subgroups? Abelian groups of order 36, let's say. Just subgroup groups of order 36. Yeah. Do you have any criteria to write it? Yeah, can anybody tell me how do you proceed? Yes, I think this has been discussed in the class somewhere. Can you recall? Yeah, any of you? Okay, so the hint is fundamental theorem of finite abelian group. This is a finite group, also abelian group. So you can use what is fundamental theorem of finite abelian group. Is anybody who remember the statement? All of you here, right? Okay, we only have two people here in this session. Okay, so it says that if you have any finite abelian group, then you can always write as a, product of prime powers, cyclic, that are anyway you can say. So that is, you can always write as product of prime powers. So 36, how would you write as a product of prime power? Can you write it? Product of prime powers. Yes.
Yes.
Yeah, how do you write it?
It's 2 squared into 3 squared.
Yeah, it's 4 into 9, and you can write it as 2 square into 3 square. So this is product of prime. So therefore you can write as all the subgroups or the groups of order 36, you can write it as product of prime powers. So what are the possibilities as product of primes? So you can just simply write as z mod 2 power 2 z times z power z into z by 3 square z. So I'll just write. So this can be written as z mod 2 square z into z mod 3 square z. This is the first possibility. Can you give me all possibilities writing this as a product of prime powers? This is product of prime power, right? This is not the only way to write as products of primes. Yes. The theorem says that you can write it as product of primes. Yes.
Yes. You can write it as z mod 2z cross z mod 2z cross z mod 3z cross z mod 3z.
Yeah, this is one more possibility. Any other way?
Z mod 2 squared z
Yeah, so z mod 2z 2 square z. Yeah.
cross uh, z mod 3z z mod cross z mod 3z.
Exactly right. This is another possibility. Any other way?
Yeah, similarly like z mod 2z cross z mod 2z cross z mod 3 squared z.
Exactly right. So how many possibilities finally we have?
4.
4. So number of abelian, number of groups of order 36 which are abelian up to isomorphic, they are 4, right? So we have listed all
Yes.
4 up to isomorphic abelian groups of order 36. Yeah, so we can simply use fundamental theorem of finite abelian group. So yeah, what can you say about part 2? You have to check whether these following groups are isomorphic or not. So this is Z mod 4Z and Z mod 2Z cross Z mod 2Z.
They are non-isomorphic. A
They are not
is non-isomorphic.
But
Yeah,
reason? What is the reason? Yes.
because Z mod 4Z is cyclic, but second one is non-cyclic.
Yeah, so you can quickly see that Z mod 4Z has an element of order 4, which is just the identity 1 element 1. However, you don't have any element of order 4 in Z mod 2Z cross Z mod 2Z, because your if you have isomorphism, that means you have a homomorphism between these groups, which will preserve the order of the group. So preserve in the sense like it should divide the order of the group, but four, you can see that there is a order of element of order 4. However, other side you don't have. So therefore, it is not the case. Okay, what about B? Same, right? You can use the same way to see that what is there any isomorphism between this? Can you tell me for B quickly, and C will be an exercise to do. Yeah, can you check whether this Z mod 6Z is isomorphic to Z mod 2Z cross Z mod 3Z? Yes. So the trick that you used for part A will not work here.
Number of elements are different.
Number of elements for part B.
Uh, no, they are same, but here, see, first one is cyclic, but second one is not cyclic one.
Why Z mod 2Z cross Z mod 3Z is not cyclic?
Because uh, 1 comma, okay.
So you have one as an element in Z mod 6Z which has order 6. Can you check whether there is an element of order 6 inside Z mod 2Z cross Z mod 3Z? Yeah. Because this is the only issue in the earlier part. One has an order 4, however, one has order 2 in part A. But can you check whether there is an element of order 6 inside Z mod 2 Z cross Z mod 3Z? Yeah.
No, 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 there is no element of order 6.
Yes. Are you sure? What if I give you 1 comma 1? Can anybody tell me that what is the order of this element inside Z mod 2Z cross Z mod 3Z? Yeah. If you remember, order of this is nothing but the order of LCM of the order of 1 inside Z mod 2Z and order of 1 inside Z mod 3Z, and you take the LCM of that. Isn't it?
Yeah, it's 6. Yeah.
It's 6, right? So
Yes.
you can recall if you have Z mod n Z where n is product of two distinct primes, as you can see in this case, then that will be a cyclic group, right? So Z mod 2Z cross Z mod 3Z is a cyclic group of order 6. And generator is this only, 1, 1. Right? You can get all your elements of this group.
Yes.
Just by,
yes.
right? So therefore, part B is true. So part A is false, part B is true. I think part C you can try using the same tricks, right? Can I leave this part? Because you can always split your, let me just give you a hint if you want to write. So if you have Z mod P1, P2, Z, where P1 and P2 are distinct primes, then you can write it as Z mod P1Z times Z mod P2Z. This you can always write, right? This you can see from part B. That if you have two distinct product of two primes, that you can separate as a product of these two groups. So you can use that fact to decompose this further, and then you can check the orders. Is that okay? Yeah. Yeah, please respond. Do you want to discuss or can we leave?
We can discuss.
Okay. Let's discuss then. So, yeah. Okay, so how will you split these groups? As I told you, in product of primes. So, do you have any such primes in decomposition here? So 54, as you can see, it is 2 times 27, and not even primes. If you have co-prime numbers, then also you can do it. And same thing for 48 anyway, you can write it as 3 into 16, right? So those are also co-prime, so you can write it as Z because you know the fundamental theorem, so it can be written as Z mod 3Z cross product of primes, so Z by 16Z times Z mod 9Z. And we want to check whether this and Z mod 8Z times Z mod 2Z times Z mod 27Z are they isomorphic. So can you now check? It's little easier now. So remember, whenever you have M and N co-prime, then Z mod M N Z, you can write it as Z mod M Z cross Z mod N Z. This is what we have used. Yeah, can you now check? So hint is one group has Z mod 16Z, other group has Z mod 8Z cross Z mod 2Z. Or for 27 also you can see. Yeah, can you write it further now? Even if you say wrong answer, you can say something. So please do respond. So for the first group where we have Z mod 3Z cross Z mod 16Z cross Z mod 9Z, does it have an element of order 16? Yeah. Yes. Can you give me one element having order 16 in this group?
Uh,
0, 1, 0.
Exactly. 0, 1, 0 is that element having order 16. Can you give me an element of order 16 in the other group? Yeah. There is no such, right? Yeah, because Z mod 8Z cross Z mod 2Z does not have any element of order 16, right? Anyway, you cannot get an element of order 16 from Z mod 27Z. So if there is at all, there is an element of order 16, you should be able to get it from Z mod 8Z cross Z mod 2Z. But at the most, you can get it 8, right? Because you can take the LCM. LCM will be 8 always. So it will never be 16. So similarly, you can say in terms of 27, other group has order element of order 27. However, you will not get an element of order 17 in the first group. So is it okay that they are not isomorphic? Uh, yes,
Yes, yes.
it's okay, right? Okay. So therefore, we can move to next question. Yeah. So question 4 says, give me an example of a UFD which is not a PID. So UFD by definition, you should have a unique factorization of any non-zero element in that ring, and PID means every ideal should be generated by a single element.
Z of X.
Z of X. Okay, why it is not a PID? Answer is absolutely correct, ZX, but why it's not a PID? So
You can take the ideal generated by 2 comma x.
2 comma X, exactly. So you can take this ideal and you have to prove that this is not generated by a single element. That is still left to prove. So you have to prove that this cannot be written as any f where f is in zx. So can you give some argument to say that it cannot be written as a generating by a single polynomial inside zx? Yeah, because this we know that this is not a PID, but what is the argument? Like, why will you say that it will not be generated by a single element? Okay, maybe we will come to this part at the end again. Till then, we can try the other question. So, answer is ZX. Can you give an example of not a UFD? That means you may have more than two factorization of the same element. Yeah, any example in your mind?
That example 1 in question number 5.
Example 1 in question number 5 gives you not a UFD.
Yes, it is not even an integral domain. Therefore, it is not an UFD.
All right. So can you give me some non with some integral domain which is not a UFD? So the answer for this is
Z of square root of -5.
exactly. So z square root of -5. In fact, you can take z square root of -6, -7, minus, I guess -7, not -6. -7, yes. So there are many. So this is one of the example of not a UFD. So question 4 is roughly done. I will come back to the fact that why it's not a PID. ZX is not a PID. Yeah. So which of the following are integral domain for question 5? You have many such rings which are written here. Which of them are domains? As you pointed out, first is not a domain. Can you give me the explanation why it's not a domain?
Because we can find two non-zero elements whose product is 0.
Yeah. So can you give me those two elements?
The images of 1 plus x and 1 plus x.
Okay. So you want to say
This
oh,
is
you
equivalent to Z2 of x over ideal generated by 1 plus x squared.
okay, can you repeat once again? Sorry, I missed your last argument.
The given quotient ring Z of x over the ideal generated by 2 and 1 plus x squared is isomorphic to Z2 of x over ideal generated by 1 plus x squared.
Exactly right. So you can establish this isomorphism Z mod 2Z times x modulo the ideal generated by 1 plus x square. Exactly right. So can you tell me why it's not a domain?
The coset of 1 plus x, the coset corresponding to 1 plus x
Uh-huh.
is non-zero.
Okay.
1 plus x is not an element of ideal generated by 1 plus x squared.
Exactly.
So therefore the image of 1 plus x is non-zero. Again take the same 1 plus x.
Yeah.
The product is going to be 1 plus x squared.
Yes.
So it belongs to the ideal, therefore it corresponds to 0 element.
Yeah, correct. So you got two non-zero element whose product is 0, so therefore it cannot be a domain, right? So you can see that if 1 plus x whole square in this case is 1 plus x square because 2 becomes 0 in z mod 2z. So therefore you got and 1 plus x square is a 0 element inside this quotient ring. Therefore there are two non-zero element whose product is 0. Therefore it's not a domain. Or you can also say that so Z2 is a field. So if you have kx modulo f, you can also say if you have kx modulo f, so that becomes a field and provided you have this as a irreducible polynomial. So here you can use also that fact or no. I guess you can simply use this fact. That is also correct. What about zx modulo 2 comma 1 plus x square? So So if you can say that this is a field, of course that is a domain, so that is easy to say. However, if it's not a field, still you may be a domain. So therefore that idea is perfectly fine. Going to find two elements whose product is 0 or non-zero. What about part B? So here you can use this fact which I just told you. It will be isomorphic to z2x mod 1 plus x square. Now what can you say further about this ring? Is 1 plus x square irreducible polynomial over z2?
Okay,
Yes.
there are two elements in Z2.
Yeah.
So for none of them, that 1 plus x squared is 0.
Yeah.
So therefore it is irreducible over Z2.
Yes.
And Z2 of x is a PID.
Yeah.
So that becomes a field.
That becomes a field, therefore isomorphic to Z2, right? Right. So therefore, this is a domain. This becomes a field and therefore becomes a domain also. Right. So you can do the similar thing for part 3 and part 4, right? Can I leave them? So as you can see, this will be z3x mod 1 plus x square, and this will be isomorphic to z3x mod 1 plus x square. Now you just simply check which of them is a irreducible polynomial and which will have roots. Based on that, you can check whether they are domain or not. So if you have roots, that means you can decompose your lower polynomial as product of two factors. That means two non-zero element can make it 0. So once you find roots, that means you can say it is not a domain. So I think for Z3, 1 plus x square is irreducible and the other one will be reducible. So part 2 and 3 are the domains, 1 and 4 are not domains. Is it okay? It's okay, right? So question 6 is just a repetition. If you
So
is K.
You say 2 and 4 are integral domains, right?
Yes, yes.
Whereas 1 and 3 are not so.
2 and 3 are domains, 1 and 4 are not domains. Did I say it wrong? Yeah, sorry, if I said it wrong, 2 and 3 are domains, 1 and 4 are not domains. So question 6, if we go to question 6, we have kx mod f is isomorphic to k, where k is a field. Is it true for all f in kx? It's the kind of repetition as we did for question 5, so you can quickly tell. So as you can see, question 2, question 5, part number 1, you can write z2x mod 1 plus x square, and that is not even domain, therefore cannot be a field. So not every f can give you a field. Only when f is irreducible, then only your isomorphism will be to a field. So I think question 6 is completely, you can take examples from question 5. So I can leave, right? You can also construct some other examples like Rx modulo x square plus 1 or Rx modulo x square minus 1. So you can also write certain different examples. You have Rx modulo x square plus 1 and Rx modulo x square minus 1. So for which one will you get a field, which one will not give you field?
X squared plus 1 is irreducible over R.
Yes, it is
Whereas x
irreducible.
squared minus 1 is reducible.
Yes. So therefore, here you can write as x plus 1, x minus 1, and this become a zero element inside this ring. And none of them is a zero element inside this ring. So therefore, it's not even a domain, therefore not a field. Is it okay, right? So we can go to question 7 now. We have to check the irreducibility of certain polynomials. So one is fx is x cube minus 2 over rx, or maybe in rx I should say. Let's say over r over q. Yeah, what can you say about first polynomial? Is it irreducible?
It's reducible in order of x.
It is reducible. Why?
Because you can write x cube minus 2 as minus cube root of 2 into x squared plus x plus 1. So it's reducible.
Yeah, because 2 power 1 by 3 is an element inside R. So
Yeah.
you can write fx as a product of two polynomials where the degrees of the polynomial are greater than equals to 1. One of them is greater than equals to 1. None of them is a unit. So x minus 2 power 1 by 3 is it's a non-trivial factor of fx. Therefore, it's a non-constant factor, I should say. So therefore, you could decompose your polynomial as product of two polynomials, and your function is not a polynomial, is not a irreducible. Therefore, it reduces into two polynomials. What about part number 2?
So this is irreducible.
This is irreducible. What is your argument to say that?
Because it is of the form x power p minus 1, etc. Where p is the prime number 5.
Okay, so let me write it once what you are saying. So you are saying that your polynomial is x power p minus 1 plus 1 till 1.
Yes.
It's of that form. And why do you say it's irreducible?
Because you can find the sum and then you can replace x by x plus 1.
Uh-huh.
And then you can apply instant criterion.
Right. So if you just quickly see, you can modify this function as f tilde x by replacing f of x plus 1. You change your x to x plus 1, your polynomial will be changed by x power x plus 1 power 4, so on, plus x plus 1 plus 1. I think it will be x power 4 plus 5 times x cube plus 10 times x square, something like that will come, plus 5. So your whatever your prime is appearing here, that only will divides all your components, and you can use the Eisenstein criteria to say that it is irreducible over Z and therefore irreducible over Q also, because it's a primitive polynomial. Also, you can see that part also anyway. So this becomes irreducible over Q. What about part third? X square plus 1 whole square in Rx.
Which is x squared plus 1 into x squared plus 1.
Yeah.
So it is reducible over Rx. So
Okay, what about
even though there are no roots in R, but
mm-hmm.
reducibility will come.
Yeah, because you could able to write your polynomial as product of two polynomials. None of them is a unit. none of them is a unit in R. So therefore, you can say that it's a reducible over R. You could reduce your polynomial as product of two polynomials. So among these, only part 2 is irreducible, rest are reducible. For question 8, which of the following is an algebraic extension?
Algebraic extension of Q.
Yes, algebraic over Q. Yes, algebraic extensions of Q.
Q of I.
Why it's an algebraic extension?
I is algebraic over Q.
Okay, and how it is an algebraic element?
X squared plus 1 is a polynomial in Q of X.
Yeah,
satisfied
exactly.
by I.
Yes. So if you can find a polynomial over Q which has I as a root, then you say I is algebraic over Q, and it is, you can see that it satisfies this polynomial over Q. So therefore I is algebraic, and every element of Q is anyway algebraic over Q. So therefore this whole extension is algebraic over Q because every element is algebraic over Q. It's okay, right? So what about Q pi square?
So pi square, pi is not an element of Q.
Yeah. Even I is not an element of Q.
So pi is a transcendental over Q.
Okay.
So that means pi cannot be an algebraic element of Q. Over.
Okay. What about pi square?
All powers of pi are not algebraic over.
Yeah, so pi square is a transcendental element. Pi cube is a transcendental element. In fact, all powers of pi are transcendental. So you will not be able to find any polynomial over Q which has pi, pi square, any of them as a root. So therefore, this extension is not algebraic. Right. So what about part 3? Q of omega, where omega is cube root of unity.
Cube root of. So x cubed minus 1.
X cube minus 1, exactly. So you have x cube minus 1. This is a polynomial over Q. You can see nicely. And omega satisfies this because anyway it's a cube root of unity. So therefore it's an algebraic extension over Q. Right. So what about part 4? Q root 2I.
Q root 2I. X squared minus 2.
X square minus 2.
Plus 2. Plus 2.
Yeah, x square plus 2. So x square plus 2 is the polynomial. So this is also algebraic extension over Q. So except Q pi square, all extensions are algebraic extensions. Okay, so can you give me one extension of R which is not algebraic? Okay, you can think of it. We can move to next part. Yeah, so we have few more questions. First is Q of I. So Q square bracket of I will just mention this is a polynomial ring in I. That means you have a naught plus a1I plus a2I square and so on like that. AIs are from Q. And Q round bracket I is the quotient of polynomials in I. You have polynomials, you take the quotient of polynomials in I. So, is those two rings are same? In fact, one is a field, other is a ring. Are they equal? First of all, uh, Q square bracket I is is this contained in this? Is this containment true?
Yes.
This is trivial because every
Divided by
element.
1.
Right? Sorry.
Divided by 1. Any
Yeah.
polynomial.
Yes. So you take any f in Qi and quotient by 1. Those are anyway quotients of two elements of Qi. One is an element in Qi. So trivially any element of Q square bracket I is contained in Q round bracket I. What about the converse? Yeah, Vaishnavi?
Yes, it will be like a plus bi by c plus di. So we can rationalize so that you can take the conjugate so that uh,
Yeah, so the idea which you are trying is completely right. You are trying to see that whether an element inside Qi is it invertible or not, right? Because
yeah,
if you can write every element of Qi as an invertible element, then quotient will be nothing but the element Qi again. Because if you try to write Qi, then you have f mod g. And this is nothing but f times g inverse. If you can write your g inverse an element of again in Qi, this is again in Qi, if you can write, then product will be in Qi. Therefore, this whole element will be in Qi. So, if you can say that your element is invertible, that means invertibility in Qi, then you can say the both the rings, in fact, both are fields. So Q is every element of Q, every element from Q, is it invertible in Qi? Yeah, Q is a field, right?
yes, yes,
So just you have to check whether I, the element I, is it invertible in Qi or not. Can you see that? Can you find the inverse of I?
Yes, it's minus I.
It's minus I. So, which is anyway in Q of square bracket I, right?
Yeah.
So, every element of Qi is invertible inside Qi. Therefore, both the rings are filled actually. And both are same. Qi is same as Q of round bracket I. Okay, using this observation, if I ask you, if I replace this I by any alpha, where alpha is an algebraic element over Q, can you say the field extension Qi, Q of alpha, is same as the ring Q alpha? So I will just rewrite this question. Is Q alpha same as Q alpha, where alpha is algebraic over Q? Yes, any one of you can say that. One is ring, one is field. Only difference is one has all invertible elements, other may not have. But if we want to check to be same, we want to say that every element in Q alpha is invertible. Then it becomes field. And you also know that one containing another. They have to be equal. Yes. First is, what is your guess? We will see whether it is true or not. What do you think? Yeah, any guesses?
They are equal.
They're equal. Yes, this is true. But can you see how?
Because if alpha is algebraic over Q, so we can find a polynomial.
Yeah, I'll write. Okay, so we have some polynomial. Let's say this is the polynomial being satisfied over Q. Then yeah, is there anybody else who can help?
So it will be in Q of Q square bracket alpha, this polynomial.
Yeah, yeah.
So
You have to say alpha is invertible. That's it. If you remember, you just need to check whether alpha is invertible. Because
yeah.
elements of Q alpha, you just need to check. In fact, it is enough to check alpha is invertible. Rest are invertible, that you know. Q, every element of Q is invertible in Q alpha. What about alpha? Is it invertible in Q alpha? That means inverse should be a polynomial in alpha. Crucial is what you have said, this polynomial. Look at this polynomial once again. Can you find inverse of alpha from there? Yeah, there is one more student. Can you help? Okay, so what do? You just simply write your A naught as to the other side. This becomes minus of A naught. Minus of A naught. Now can you do something?
Uh, yes, we can take alpha outside.
Exactly. You take alpha outside, you will be a1 plus so on an alpha n minus 1 equals to minus a naught. Now, can you do something?
Uh, we can take inverse of a naught.
Yeah, just exactly. So
Minus
you
a, yeah.
right. So what do? You just take minus a naught this side, and this becomes 1. Now inside this alpha time this is this an element in Q alpha?
Yes,
This
yes.
is a polynomial, right? Because your coefficients are from Q. So therefore, alpha is invertible. And therefore, alpha, you can say that whenever alpha is algebraic, then Q alpha, the ring Q alpha is same as the field Q alpha. So this is true. Now we go back to question 7 now. What is this degree of this field extension Q root 7 over Q?
Seven.
Degree 7?
Yes.
No. Can you please check once again?
Uh, it's degree 3.
Degree
So
two.
degree 2, right?
Two.
So yeah, why degrees 2?
Because root 7 is algebraic of degree 2 over Q.
Yeah, so which the polynomial it satisfies is x square minus 7. And this is the smallest polynomial. I mean smallest in the sense that by degree you can find various polynomials satisfying by root 7, but this is the smallest degree polynomial which satisfies by root 7. Therefore this is an irreducible minimal polynomial for your root 7, and the irreducible polynomial satisfied by root 7, that you say that the degree of the polynomial is same as degree of extension, so it is 2. Yeah. What about other? Question part 2. This is 2. Not able to write. Okay. What about qx mod x5 plus 5x square plus 10 is to q? First of all, does it make sense? Because we only talk about field extensions. Is the given ring which we have written, is it a field? This is a polynomial ring in Q, modulo some ideal. Is it a field?
Yes, it is a field because it is p value 5.
Right. So using
Einstein
Eisenstein
criterion
criterion.
satisfied.
Right.
So irreducible.
Right. Right. So qx mod x power 5 plus 5x square plus 10. This is actually isomorphic to Q. Sorry, what did I say? Sorry, this is a field, right? This is a field. But what can you say about this extension? This is not isomorphic to Q, sorry. But this is a field. What can you say about its degree? Yeah. So hint is you look at question number part 1 again. You can write your q root 7 as isomorphic to qx mod x square minus 7. Can you say that?
Q root x is isomorphic to
Q root 7 is isomorphic to Qx mod x square minus 7. If you are not familiar, let's leave. Okay, so we can think about other way. So you know that if you have a field that you know that this is a field, Qx mod x power 5 plus 5x square plus 10 is to Q. This is a field, right? If you know that this is a field, then it should be a vector space over Q. If it is a vector space over Q, it should have a basis over Q. So can you try writing a basis for this extension over Q? Maybe I will just, you don't know, then let's leave then. This you know that if you have a irreducible polynomial, then adding roots of that irreducible polynomial to your base field Q will give you a extension of Q, right? But finding roots of this 5-degree polynomial over Q, or that will be very difficult. But at least you can try writing a basis for vector space, and from looking at the dimension of the basis, you can tell the degree of this extension. So if I ask you, can this ideal contains any linear polynomial in Q? Can it contain?
no,
Can it contain a square polynomial?
no,
Q polynomial?
no,
Degree 4 polynomial?
no.
So can you write a basis now? So if I try writing a basis for this, then if you write this as an ideal, then you can write basis I, x plus I, x square plus I, x cube plus I, x4 plus I. Can you write this? And if I say x power 5, can you write that x power 5 as a combination of these? If I want to know whether you can write x power 5 plus I.
Yeah, we can write.
You can
Yes.
write, right? You can write.
Yes.
So therefore, later after power 4, you can write it as a combination of these 5 elements. So these should be the basis. Can you check that this is a basis? This will like take some time, but you just try proving that this becomes a basis for. It's a linearly independent set, it's fine, but is it a spanning set? That you have to write. That means any f plus I you can write as a combination of these elements. Convince yourself that this becomes a basis. Is it okay?
Basis over Q. Okay.
Yeah. Over Q. Field is Q. That means any fx plus I, you can write it as a combination from Q. A naught into I plus A1 times x plus I, and so on, where AIs will be from Q. This is how you will write, right? So check, it's a basis, and therefore what is the dimension?
5.
Yeah, so 5 will be then the degree of this extension. So does it sound fine, or you still need some explanation? So if maybe we will quickly do this question, we can go back and we can prove that this is a basis. Okay, so let's do other things and then we can, if we have time, we will come back. So what about R over Q? What is the dimension for this? You can see as a dimension infinity, right? So you can see either it's a field extension or you can see as a vector space also, because if you have Q field and you want to look at all extensions, then they will be nothing but the vector space over Q. So you look at the vector space dimension and why it is infinity. What is the basis? Means, can you give me a linear independent set here which has infinite dimension? Because every linear independent set you can extend it to bases. And if you have infinite dimensional linear independent set, then of course bases have to be infinite dimension. Do you follow what I said? Yeah. Can you give me a linear independent set which has infinite dimension? I mean, cardinality, it has infinite many elements. Yeah, Vaishnavi?
You can take one square root of x, square root of 2, square root of 2 squared, and
Square of
these are
2 square will be 2 and then you will back in Q, right?
yeah.
Can you give me an element in R which is maybe transcendental? I should then everything will be given to you anyway. Some transcendental element.
So pi squared, pi cube, etc.
Yeah, so then you have this linear independent set pi square, pi cube, and so on. So you cannot write any of them as a combination of others, right? You cannot write because your scalar should come from Q only, and you are not allowed to take pi. Therefore, pi square you cannot obtain from pi. Pi cube you cannot obtain from pi square pi, and so on. Therefore, pi square, pi cube, so on. This is a linearly independent set of infinite cardinality. Therefore, basis has to be either this or more than this. Therefore, this is infinite. Okay, so what about part 4? Q zeta p over Q, where zeta p is the primitive pth root of unity in C.
P.
It's P. Is it sure you are P? Think a while, maybe you will get it.
In P minus 1.
Yeah, it's P minus 1. Why 1 less?
Because psi p satisfying x power p minus 1
Yeah,
polynomial.
yeah,
And if you factorize it, you will get x minus 1 into another p3 degree polynomial.
yeah, right. So
So that
exactly.
psi p will not satisfy x minus 1 because it is a primitive pth root.
Yeah.
Therefore, it will satisfy the p minus 1th degree polynomial.
Yeah. So since you have this primitive, so it will not be 1. And you can write your polynomial as product of these two factors. These are not a unit in Q. Therefore, this is a reducible polynomial. Also, the psi p, where p is a primitive root of unity, it will be satisfying by this polynomial, the degree p minus 1 polynomial. Therefore, and it is irreducible, by Eisenstein criteria and change of variable. Therefore, degree is not p, but it is p minus 1. So this is p minus 1. Right, so we are done with question number 10. Question 11, can we use some result on field extension to check whether root 3 belongs to q 3 power 1 by 5? Maybe not a result, but some fact on field extensions. Some facts. Yeah, can you say? Maybe I will give you some hint. You have this q and you have this q 3 power 1 by 5. If root 3 belongs to this, but you know that root 3 belongs to q?
No.
So you have another extension, q root 3. And if root 3 belongs to q 3 power 1 by 5, can I say that q root 3 is an extension, q 3 power 1 by 5 is an extension of q root 3? Yeah, just like you
cannot
have.
get root 3.
So that's suppose, no, this is what I want. Suppose we say that root 3 belongs to this, right? Just like we have q is contained in q root 3. If root 3 belongs to q 3 power 1 by 5, then q 3 power 1 by 5 becomes an extension for q root 3, right? So this is an extension, this is an extension, this is an extension. Does it make sense?
How that q3 power 1 by 5 is an extension of q root 3?
Yeah, so in order to say an extension, that means that q should be contained in q 3 power 1 by 5. Then only we say it is an extension, right?
Yes.
If root 3 belongs to q 3 power 1 by 5, then q root 3 can be sit inside q 3 power, right? Then this implies q root 3 is contained in q 3 power 1 by 5. If this is true, can I say that? Look, q is contained in q 3 power 1 by 5, right? If I say root 3 also belongs to q 3 power 1 by 5, then this whole q root 3 contained in q 3 power 1 by 5, isn't it? Yeah, Vaishnavi?
Yes, yes.
If this is okay, then can you find some contradiction from here? Do you know the finding the degrees of tower of fields? If we have two, yeah,
q to q3 power 1 by 5 is of degree 5,
yeah,
which is an odd integer.
yeah.
So you cannot get the product of two integers equal to 5.
Yeah, because you know that this is what? This extension is what? What degree?
2.
It's a 2 degree. So can you find
Yes.
certain element like this equal to 5? Can you say?
No, because it cannot be a fraction.
Yeah, your degrees
Like
cannot be fraction. It has to be degree of certain polynomials over Q. Exactly. So therefore, What is the final answer? Does it belong to this or no?
No.
No, it does not belong. Right. What can you say about question 12? Suppose you have an element K in K, A in K. K is your field. Any field. Why any element A over K is algebraic over K?
Because it satisfies the polynomial x minus a.
Yeah, very right. It's just right x minus a where a is in K. So it's a polynomial in K, right? Because your coefficients are from K. 1 and minus a both are from K. Exactly right. So every element of K is algebraic over K. Just like you have every element of Q is algebraic over Q, and you just check element alpha whether that is algebraic over Q. Because you don't need to check an element of Q from Q. Okay. Now question 12 is done. Question 13.
Is it necessary that K must be a field?
Because we only talk about algebraic elements over
Okay.
field, right? Yeah. But there is one more terminology called algebraic integers. For that you have to look at monic polynomial. But we will not go into that. But that makes sense over rings also, over Z also. But we are just looking at algebraic numbers. We need fields over Q. So yeah. Question 13, you need to determine whether or not the following extensions are splitting fields. So what are splitting fields, first of all?
Smallest field extension containing all roots.
Containing all roots. So if I say F3x, F3 is the finite field of order 3, F3x by ideal generated by x power 5 plus 1. What can you say about this? I mean, is this splitting field for F3 over F3?
Yes.
How?
So F3 contains only 3 elements.
Yeah, 0, 1, 2, right?
So if we take any polynomial,
First of all, in order to check whether you have splitting field, it should be a field, right? Is F3x mod ideal generated by x by 5 plus 1, is it a field?
Yes, because x power 5 plus 1 is irreducible over f3.
If I say x equal to 2, what is x equal to 2 for this polynomial x power 5 plus 1? If I take x equal to 2 for x power 5 plus 1, what will be the polynomial then? 2 power 5 plus 1, what is that?
0.
It's a 0 under F3.
0.
Yeah, so this is not even a
Field.
not even a field. Therefore, you cannot even talk about this being a splitting field for F3. So anyway, first one is just to check whether you know about fields or not. Question part 2 is Q contained in Q root 2 for the polynomial x square minus 2. Is Q root 2 a splitting field over Q with the polynomial x square minus 2? Yeah, what are the roots for the polynomial?
It's plus or minus root 2. Yeah, it's a
Yeah.
splitting field.
Yeah.
Contains
So it's
all
a
the roots of the.
right. So Q root 2 indeed a splitting field for Q over for the polynomial x square minus 2. Right.
Smallest
So
field.
yeah, can you find the smaller than this, which contains all roots? Yeah. What is the definition of Q square bracket root 2?
That is polynomial ring.
It's a quotient field, right, of polynomials in Q root 2, right? Q root 2, ground bracket 2, this is a field, right? And another definition is it is the smallest field containing Q
Containing.
and, right? So therefore it is indeed the smallest field containing the roots of this polynomial. So yeah, this is a splitting field. However, if I say Q root 2 root 3, what do you say about that? This
No,
is not
it's not
smallest.
smallest. Yeah,
Yeah.
smallest.
So issue is this is a smallest field containing Q root 2 root 3. But it is not the smallest field containing just root 2 and Q. Right? So therefore, this is not splitting field. However, Q root 2 is a splitting field. Okay, so question 14 is why the splitting field for x power p power n. So we have x, p, and then power n minus x over finite field fp. Why this has exactly p power n roots? So as you can see, this is a polynomial of degree p power n, right? It may or may not have all distinct roots. But can you say why it's a splitting field should have all distinct roots? So maybe I'll just give you, before this, I'll give you some examples. So if you look at, um, let's say, x cube minus 2, and we look at Ri over R. Is Ri a splitting field for this polynomial over R? Yeah. So
Because
what are the roots? Sorry?
x cube minus 2 has one real root and two imaginary roots.
Yeah.
Those two imaginary roots are conjugates.
Yeah.
And both are in Ri.
Yeah.
And Ri is the smallest field containing these three roots.
Yeah, exactly. So it's a splitting field, right? But you can see the roots of this polynomial, right? You don't need to take all the roots from the polynomial in order to construct a splitting field. But why this polynomial x p power n minus x? You should contain all p power n roots in order to write a splitting field. Why it has all distinct roots? This is what my question is. So suppose, yeah.
All these roots form a group.
Okay, and how do you say that the group has p power n elements only? Why not less?
Order of each element is p power n.
Okay. So okay, maybe I'll repeat. So what I want to say that it does not have repeated roots. Just like you have what should I say, x square plus 1 whole square, it has repeated roots, right? Why this
So that
polynomial?
means this polynomial and its derivative should have a common root.
Yes, very, very true, right? So the issue is about its polynomial and its degree, derivative. So you have this polynomial. What is its derivative?
P power n, x power p power n plus 1.
Yeah. So can you say that these two polynomials have same root? First of all, your first polynomial 0 is a root in that, right? Is 0 a root in the
Yes.
derivative?
No.
No.
No. Other root of your first polynomial are p power n minus 1th root of unity. Right? So rest of the roots satisfy xp power n minus 1 to be 1. Do you agree with me?
Yes.
Can you use this fact to say that derivative will not be 0 for those polynomials, for those elements? It's very simple, right? You just plug this property in derivative. Okay, so when you look at your derivative f prime x, if you write x power p power n minus 1 to be 1, suppose that is the root which satisfies this polynomial, then you will get p power n into 1 minus 1. What can you say about this polynomial inside fp, finite field fp? For those x which are zeros of the p power n minus 1th root of unity, can we say that derivative is 0 or non-zero? What is the characteristic of finite field fp?
It's P.
It's p. That
Yeah,
factor
it's
becomes 0, right?
yeah 0. It's minus 1. So P
Is it,
minus 1.
is it 0?
No, no.
It's never 0, right?
Yeah.
So therefore your roots are never repeated. All the roots are distinct. Right? Therefore, if you add roots of this polynomial to finite field fp, you will get a n degree extension of fp. Do you agree? Just some side remarks. So if you have this roots of this polynomial and all are distinct, and if you have, if you add all the roots to your finite field, you will get an n degree extension of finite field fp. Right? Okay, so now last question, you want to know the algebraic closure of a field. What is an algebraic closure of a field?
First, it is algebraically closed.
Okay, what do you mean by algebraically closed?
So any polynomial over that field has at least one root in that field.
Yeah, and
Second condition, that K is an algebraic extension of some subfield F.
okay,
So when those two conditions are satisfied, we call K as a algebraic closure of F.
right. So can you give me an example of a field which has C as its algebraic closure?
or
R. Any other field?
Q.
Sorry, Q is not the field which has C as its algebraic closure. Can you think a little bit more?
R of I.
R of I is anyway C. That is
C.
just C.
Okay.
Yeah,
C.
that is just C. So for us, at least R is an example, but Q is not a field whose algebraic closure is C, because C over Q is not an algebraic extension. And reason is you have pi that is element of C but is not an algebraic element over Q. So C over Q is not an algebraic extension, but C over R is an algebraic extension and C is algebraically closed. This is fundamental theorem of algebra, and therefore C is an algebraic closure for R, right? Okay, now we have 5 more minutes and we can go back to that one fact that we discussed is maybe which one was that we have discussed? Yeah. Why ZX is not a PID? You told me 2 comma X is an ideal, and why it's not generated by a single element? I will write the proof now. So just give me a minute. Yeah. Right. So I guess all of you can see now. So we want to know ZX is not a PID. And our claim is X comma 2 is not a principal ideal. First of all, can you check one thing, that is X comma 2 is whole of ZX? Can you say that? Can you say that completely this ideal is the whole ring? Yeah.
3
Yes.
3 is not there.
Why 3 is not in the ideal?
Because if it is possible, you can write 3 equal to AX plus 2B.
A is means you means fx, right? Because your elements are from the ring.
ZX.
Now, what is the issue?
So that X into f of x must be 0.
Yeah.
X into f of x must be 0. Okay. So 3 equal to 2 times gx.
Why? Because it's a polynomial from Z. So if you have any polynomial, then AIs are from Z. The only possibility is 2A naught is 3, where A naught is from Z. That is not possible. So therefore, you can say x comma 2 is completely sitting inside ZX and it contains X. You can say that this is a maximal ideal. There is nothing in between, that also you can check. Now, this is one fact that we want to say. Other fact is we want to say that this is not written as any polynomial px where px is in zx. Can you say something from here? If this is so, then what can you write about x? What can you say about 2? X will be px times fx, right? And same 2 will be px times gx. For some fx and gx from zx. Can you say that? Yeah. Are you with me?
Yes.
Okay, can
P
you
of
say
x and
some?
P of x and G of x are constant polynomials.
Exactly. Now,
Yeah.
So the only possibility either 2 1 or 1 2.
constant polynomials. So in particular, your px has to be a constant polynomial. So it has possibility. Can I say this? Because you can choose gx. For this case, you can choose gx to be plus minus 2. And for this, you can choose your gx to be plus minus 1. Do you agree?
Yes.
Remember, this was the case. Now, can you say more? If your px is plus minus 1, what can you say about ideal generated by px?
It's whole.
It's
Whole Z.
completely zx. Exactly right. Very nice. So therefore, this is not possible. So possibilities are plus minus 2. Now, can you say something? Go back to your x fact. You have not used fact this. X equal to plus minus 2 fx. Can you say something now?
F of x is a first degree polynomial.
Okay.
So if P of x was plus or minus 1, so the ideal generated by that will be
Yeah, for this is zx, right? But if you take this, then what will be the ideal? It is like all polynomials with coefficients as even coefficients, right?
yeah, x will not be there.
So can you say something now? This is a contradiction, right?
Yes, yes.
So I think all the possibilities are not possible, and therefore you can say that you cannot write x2 as a single generated by a single polynomial in zx. Do you agree? Yeah.
Yes.
And now I will leave one exercise to verify. If you have, let's say, any kx and k is any field, and you have a polynomial which is fx and degree of fx is d, let's say, and f is irreducible, then please check once. Otherwise, we will prove next time that it is, let's say this is I, then the base is, so if it is irreducible, then you know that L is a field. This implies L is a field. And basis of L over K as a vector space is the following: I, x plus I up to x power d minus 1 plus I, where d is the degree of your polynomial. This is a basis. So is the statement, at least, can you follow the statement? Yeah? Are you with me?
Yes.
Okay.
Yeah, yeah.
Okay. So with this, I think I will leave. Otherwise, this will be the first question that we will discuss in the next tutorial. If this you will not be able to see, I will discuss.
Excuse me, how that x is equal to plus or minus 2? F of x is a contradiction.
Yeah. So you will get only x to be as equal to plus minus 2. Can you get x from this?
Yes.
For any fx in zx.
Oh, integer.
Right? Now, can you see?
Okay.
Yeah. Okay. Yeah. So for this, with this, I think I will stop. And you have, if you have some more doubts, you can ask. Otherwise, we will stop.
Can you explain that 14th problem once again?
14th
Excuse
problem.
me.
Okay. Let's go back to 14th problem. Yeah. So splitting field. We want to know the splitting field. Why splitting field has all distinct roots? So if you have Q and you want to know the splitting field for this, let's say this polynomial x square minus 5. Then how do you get the splitting field? You have to add the roots of this polynomial to Q, right?
Yeah, yeah.
What are the roots here? X is plus minus root 5. So if you add root 5 or minus root 5, both are in fact enough. I will add Q root 5. So it will contain minus root 5 also, because it will contain alpha time any root 5 where alpha is in Q. You can simply take alpha to be minus 1. Now this is a splitting field now. Now question is, you want to know this, you have polynomial is x power p power n minus x. This is in fpx. This is your finite field polynomial in this range. Now you want to say why your splitting field means whatever extension you will take your of fp, let's say L. Why L should have all p power n distinct roots. Now degree of your f is p power n, right? So your field may or may not have all the distinct roots. I mean to say, let's say I will give some example. Suppose you will have q and you will say x cube, let's say you have r and you have r I. You know that this is the extension for this polynomial. If you take this polynomial, this is the minimal splitting field. Now you know that you just add one root to it, not all roots. But here what I'm saying that all the roots you have to add in order to get the splitting field. All the roots. Why? Because your all roots are distinct first of all. So now you need to know that why these roots are distinct, why it has p power n distinct roots. So in order to say distinct roots, your suppose your f has repeated roots, then this implies f and f prime have a common root. Do you follow this?
Yes, yes.
If your f is like x plus 1 whole square, then derivative is x plus 1 and therefore both have x equal to minus 1 as a root.
Minus 1.
So if you can say that f and f prime have no common factor, then f cannot have multiple root. Do you agree? Is this
Yes.
statement okay?
Yeah.
If that is so, then look at fx. It is x p power n minus x. What is the derivative?
It's Pn x power Pn minus 1.
P power n and then minus 1.
Yeah, minus 1.
Minus 1. Now, you know it has roots like 0 or any alpha such that alpha p power n minus 1 is 1. Why? Because you can write this polynomial as x time x p power n minus 1 minus 1. Do you agree?
Yes, yes.
This you agree. Therefore, roots are
Yeah.
either this or this. Now, this is the set of roots. You have to check each one that whether these roots are there in f prime x or not. If you look at 0, f prime 0, this is minus 1. This is not equal to 0 in fp, right?
Yes.
for any prime, any prime. If I look at f prime alpha, where alpha is this root, I don't know explicitly, you can write explicitly, but we just need that it should be satisfying this property. Then I want to check whether f prime alpha is 0 or not. So I will simply take alpha p power n minus 1 minus 1. Now we can use the fact that alpha p power n minus 1 is 1. Is it okay?
Yeah. Yeah.
So
Yeah.
here we will put p power n times 1 minus 1. But you know p time anything is 0 because your finite field has characteristic p.
Yeah.
So this becomes 0. You will left with minus 1. This is also not 0. Therefore, any of the root of your f is not a root of f prime. Therefore, they don't have any common root. Hence, all the roots are distinct. Do you see that?
Yeah. Yeah.
Therefore, no root is a multiple root. Therefore, you need to add all the roots in order to get the extension. So this is what I have written, that you have to add all the roots. Splitting field should have exactly p power n roots in order to get this. Is it okay now?
Yeah. It's
So if no other doubts, then we can stop. Okay. Can we stop, or do you have anything else to ask?
Excuse me.
Sorry.
As you did in the last two problems, you can do all other problems like that.
Sorry, I didn't get it.
So instead of just explaining orally, we can put it in black and white.
So, okay, but I still
So
didn't
problem
get it.
followed by solution. Then you
Yeah.
write another problem followed by its solution.
Okay. So this is actually just to show them, show you the questions, and later we can see the solutions. Okay, so anything else?
Thank you.
Yeah, okay.
yeah. Thank you.
Okay, thank you.